talk about angular momentum, we're going to look back to linear momentum. Linear momentum is the product of mass times velocity. Angular momentum is like this, except it involves a rotating system and rotating coordinates about an axis. In a rotating system, the analogous term for mass is moment of inertia. The analogous term for velocity is angular velocity. Angular momentum is the product of an object's moment of inertia and its angular velocity about the center of mass. It is also called spin angular momentum and is denoted by the letter L. It operates by the law of conservation of angular momentum, which states that momentum is conserved in a closed system with no external net torques applied to the system. This equation is always true as the definition of angular momentum, because momentum is always conserved. To understand this topic, consider a skater doing a spin on the top of her skates. As her arms are outstretched, she's rotating at a relatively low speed. Her angular velocity is small and her moment of inertia is large. However, when the skater brings her arms into her body, she begins to spin much faster. When she pulls her arms closer to her body, her axis of rotation decreases, so her moment of inertia decreases. Thus, she has a smaller moment of inertia and a larger angular velocity. Since angular momentum, L, is equal to I times omega, this remains constant without an outside torque. As I decreases, angular velocity omega must increase by the same factor by which the moment of inertia decreases.
Okay, here I will apply a net torque for a specific amount of time, maybe around 3 seconds. Courtney will be receiving this angular impulse, which will cause a change in her angular momentum.
Once I'm moving, since my momentum is conserved, then if I increase my moment of inertia, I will have to decrease my angular velocity. And if I decrease my moment of inertia, my angular velocity will increase.
Here, we will demonstrate.
This is decreasing, increasing.
Notice how she slows down.
Thank you. For this example, we are asked what the angular momentum of a 0.210 kilogram ball rotating on the end of a string in a circle of radius 1.10 meters at an angular speed of 10.4 radians per second. To calculate this angular momentum, we first use the equation L equals I times omega. The formula for moment of inertia of a thin hoop produced by rotating the ball around the string of radius r is I equals mr squared. Therefore, I equals 0.2541 kilograms meters squared by substituting in the values for the mass of the ball and for the length of the string. We are given that the angular speed is 10.4 radians per second. So multiplying out, you find that the angular momentum is 2.64 kilograms meters squared per second. Referring to the answer, you get that that's correct.
What is this? Rotation.